Okay, so nobody heard me say happy birthday to Natalie. Happy birthday to Natalie. Okay. Okay. As I was saying, what we've done thus far in the class has been giving increasingly complicated algorithms that individual players in some interaction can use to get increasingly sophisticated guarantees, maybe culminating with things like swap regret and adaptive regret and more generally subsequence regret, that gave us things like convergence to correlated equilibria if everybody was doing them. But because the algorithms were increasingly complicated, you had to solve in general, like an arbitrary min-max problem at every round, it maybe becomes less and less reasonable to think that everybody will be doing this. You have to sort of assume a great deal of sophistication on the part of the agents who are interacting in this game to think that they're all going to be playing, even multiplicative weights, but like especially, something that's guaranteeing no adaptive regret, no swap regret. Those algorithms are kind of complicated. Okay, like probably in large interactions and the kinds of games we've talked about, might really have many participants, things like these online shortest paths. If you think of this as a game describing, people deciding how to drive around Philadelphia, say, like these people are not running algorithms. They are probably using, reasonably simple heuristics. They're, like looking up traffic reports according to Google Maps and just doing what Google Maps suggests, or, at best, computing, a route they think is going to have low traffic given the, given the predicted condition. And so I want to shift focus a little bit from thinking about the design of sophisticated algorithms that every person in some interaction could run, that would give them good guarantees, to algorithms that maybe some central coordinator who might have some algorithmic sophistication could run, that would make predictions to many agents, would say things like, here's what I think the traffic congestion is going to be on the roads in Philadelphia tomorrow, such that if the agents can be assumed to be not that sophisticated, but will maybe just best respond to our predictions. We'll treat our predictions as if they are correct. Right? Computing a best response is a lot easier than computing an equilibrium. That in that event, we will have guarantees comparable to those we would have had all of these individual agents been, running their own sophisticated algorithms, even though now they don't have to. They're just sort of behaving in a straightforward way. They're just best responding to predictions. We'll ask when we can make predictions that give them those kinds of guarantees, and whether it's actually a good idea for them to follow those predictions, right? Like if we're making these predictions, like, and you are a sophisticated user, like maybe you should do something else. Okay, so those are the kinds of questions I want to ask. So to set this up, I want to do a couple of things. So maybe I'll give you like a roadmap of what we'll do, not just today, but over the next, maybe 3 or 4 lectures. Okay, so first of all, I want to just like write down a model that we can agree on sort of what it even means to have like, what it even means to have different downstream decision makers who might be consuming predictions that we make in ways that are different. Like the different downstream decision makers might have their own interests. For example, in a routing game, driving around Philadelphia, the different downstream decision makers live in different places. They work in different places. Which paths are interesting to them differ across these agents, but we want, a single set of predictions to somehow be usable by all of them. So we need some model for that. We'll do that today. Another thing I think we'll be able to get to today is just, let's start with an easy set of goals. Okay. So eventually we maybe want these downstream decision makers who, even if they thought about it really hard, would have good reason to follow our predictions. And, when they did so, would have strong guarantees, things like swap regret guarantees. But maybe as a warm-up to that, we can ask, okay, well, what if we don't worry about giving them good reasons to follow our predictions? What if we just assume they're going to follow our predictions? What can we say about their performance then? And maybe we won't start with more sophisticated things like swap regret. Maybe we could just ask, if we can assume that these downstream agents are going to follow our predictions, how can we make predictions so that they just have no external regret? Okay, how can we make predictions so that they just do well according to the first metrics we've studied? Okay, so that's what we're going to try to do today. Okay, and then we're going to try to go beyond that. And, just as we had this sort of general multi-objective optimization framework in which we derived algorithms that let us eventually turn the crank and get out adaptive regret and groupwise regret and swap regret kind of algorithms. We're going to define sort of a basic algorithmic primitive that is making forecasts of some high dimensional state that satisfy a condition that is basically the forecast should be statistically unbiased, subject to various conditioning events. Okay, we'll sort of derive algorithms for sort of a basic primitive, okay, this making unbiased forecasts, and then we'll see how to instantiate this primitive in various ways that let you make predictions that not only are a good idea for people to follow, but that give them strong downstream regret guarantees. Okay, Eshwar. Sure, go for it. That's right. Yeah, good. So suppose there was just one downstream decision maker that I was worried about. And my concern about him was that he was somehow too stupid to run, like a no swap regret algorithm or something. But that he, maybe trusted me. Well, one thing I could do is I could just run the algorithm for him, and then I could just tell him what to do every round. I could be like, hey, today play action 5. Okay, hey, today play action 7. And of course, like from the point of view of analyzing his regret guarantees, like, we, the person proving the theorem, don't care on whose computer the algorithm is being run. We don't care if it's the central coordinator or the agent. So that would be one way to give a single downstream agent no regret guarantees. Yeah, so you're exactly right. This will be an interesting problem exactly because we're going to, the same set of forecasts somehow are going to be consumed simultaneously by multiple downstream agents that might have different utility functions, and we might not know what they are even. Okay, so that's going to be, yeah, that's why we can't solve this problem just by like running the algorithm ourselves and like, telling the agent what to do. It's because we need to produce information that is simultaneously useful in some low complexity way, just by like computing a best response according to some unknown utility function downstream for many agents who might have many different utility functions.
One that we like, and both the signals from examples of the coding the their part.
You mean I could just like build a traffic light and like tell people? Yeah, so if I knew it, yeah, right. So you're saying like a generalization of this thing where, if I know, if I know I'm just communicating with you, I could just tell you what to do. If I know I'm communicating with n people with n fixed utility functions, I could just send n messages and tell each of them what to do. That's right. So we want we want to not have to do that. We want to not have to know who has what utility function. We want to be able to just broadcast something. Good questions. Good. So questions about the basic motivation for what we're going to be doing in the next part of this course? All right. So we need to think about how we're going to model decision makers in order to even formulate the kinds of problems I just mentioned. So let's write down a model. So a decision maker is defined by a collection of actions A, okay, so the things that they can do. A convex state space C, which we'll assume is, it consists of some subset of d-dimensional vectors. These are the things that are decision relevant to the agent. This is how you summarize for them the information they need to know about the world in order to figure out what the payoff of their actions are. Okay. And finally, a utility function. U, which maps actions and states to numbers, to utilities, which will just, without loss of generality, scale to be numbers between 0 and 1. Okay, so my utility depends on what I do. It also depends on something that is not under my control. This could be things like what the other players in the game do. This could be things like some summary statistic of that, like what the congestion is on each of the roads in my local road network. It could be various things. The point is, I control the first argument of this function through my actions, but not the second argument. And importantly, if I want to figure out like what I should do to maximize my utility, I need to know something about what's going to go into the second argument. I need to know something about the states of the world. Yeah. So yeah, good. So foreshadowing a bit, like the kinds of algorithms we're gonna provide are gonna do things like try to predict what the state of the world is. So the presumption is that although different decision makers are going to differ in their utility functions and maybe their action sets, the thing that is payoff relevant to them is the same. So like I predict traffic in Philadelphia, for example. Good. Okay. And I'm gonna okay, so this is like a general model. I'm gonna make a technical assumption on these utility functions, basically for the entire this entire section of the class. So we'll assume that for all actions A, if I look at the utility function where I plug in action A, it's now a one argument function. So we're thinking about how this utility function depends on the state of the world. We're going to assume that this function is linear and L Lipschitz in the state of the world. By which I mean, what do I mean by Lipschitz? This is going to be in the L infinity norm. I mean that for any pair of states, SS prime, for any A, if I look at the difference in utility when I play action A and the state is S compared to what it is when I play action A and the state is S prime, this is going to be at most L times the difference between S and S prime in L infinity norm. Okay. Okay, so and so I want to think about what we can model with this, right? Because as soon as I assume something is linear, you might become suspicious that I've like severely restricted the scope of the problem, right? So like, what can I model with like a linear utility function? Okay, so first of all, you might note that if I was only talking about a single downstream decision maker, this would be without loss of generality. I haven't limited the thing at all. How come? Well, how could I, say you've got some arbitrary utility function, okay, at every day, depending on something, that just tells you for each of your actions what your utility is. Okay, not linear in anything. It's just some utility function. If I just set the dimension here to be equal to the number of actions, then one thing I could do is I could just say, okay, well, coordinate I of the state is just the utility, whatever that is, that you get for playing action I. Okay, and then, like your utility for playing action 1 is just equal to the first coordinate of the state. Your utility for playing action 2 is equal to the second coordinate of the state. That's linear. And so the linearity assumption is without loss there. Okay, so what else could it model? Well, okay, so like that's true. Like if we only have a single decision maker, we haven't. That's linear and Lipschitz, by the way. It's one Lipschitz. So if there's just a single decision maker, these assumptions are like without loss of generality. Okay, but in motivating this, like my whole premise is there are sort of multiple decision makers, and so okay, maybe it doesn't quite make sense to just try to literally encode their utility for each action in the state unless they all have the same utility function. So what else could this include? Well, maybe there's some underlying state of the world that is relevant to you. If you knew what that was, you'd knew what to do. So maybe, just to give like a toy example, you're trying to figure out what kind of weather gear to wear, when you go outside today. And like, it depends on what the weather's going to be like, right? Like it might rain, in which case you might want to bring an umbrella. It might be really cold, in which case you might want to like bring a poncho or something. There might be like a tornado or like a, some other disaster, then maybe you don't want to go out at all. Okay, there's all sorts of things that could happen. You might have different utility for each of those things, again, in an entirely unconstrained way. And then the thing I could try to forecast, the state of the world that would be relevant for you, is just a probability distribution over these different events. Like, what is the likelihood it's going to rain? What is the likelihood it's going to snow? What is the likelihood it's going to hail or tornado or whatever? These don't even have to be disjoint events, right? Like, they don't have to sum to one. It could rain. I'm just forecasting the probabilities of these different things. And then again, you've got some arbitrary utility function conditional on what the weather events are. I don't need to assume anything about what it is, but if I tell you a probability distribution over those things, your expected utility will be linear in the weights of that distribution. Okay, so again, you could care in arbitrary ways about an arbitrary set of D downstream events. If the state of the world is just the distribution over those events, that's a linear utility function. Okay, maybe just one more example that's sort of obvious. In these in these online linear and combinatorial optimization games, like online shortest paths, for example, driving around Philadelphia, sort of by definition, there is a state of the world that is a sufficient statistic for you to compute your utility function, that your utility function is linear. Remember, what did these online combinatorial optimization games look like? You had an action set that was really big. Okay, so now, like, we wouldn't want to set the dimension of the state of the world to be equal to the number of actions you have. It's like really big. It's the set of all paths, say, in the Philadelphia road network. But like the utility that you get for taking some path is or the disutility, the cost, is the sum of the costs of the edges on the path. Okay, so again, the relevant state of the world would be things like congestions for each road network in Philadelphia. D would only have to be equal to the number of roads in Philadelphia, not the number of paths. And your utility function for any particular choice of path, that's your action set, would be a linear function of this, would be a sum over the congestions on the roads that you take. Okay, all of these, by the way, still like one Lipschitz. So, okay, so I just want to point out that, you know, it might look like I'm sneaking in like a really restrictive assumption here, but this is actually not that restrictive. Okay. So, questions? Okay. So, all right. So like, you know, here you are, you're a decision maker. If you knew the state of the world, if you knew the relevant state, you could best respond to it. You could figure out what action you could take that would maximize your utility. Okay? The reason why, in general, it will be difficult for you to figure out how to act, right? The reason why, when we were designing algorithms for the agents themselves to act in ways that guaranteed them various kinds of no regret guarantees, like there was something to do, is because you need to act before you know what the state is. Okay, so like if you knew the state, you could just best respond. The whole point of all of these like no regret algorithms is to give you guarantees where you only learn the sort of payoff relevant bit of information after you choose your action, right? You choose your action, only then does the adversary reveal their cost factor. Okay, so you know, like that's the difficulty. Like you don't know what the state of the world is, and so the kind of algorithm we're going to be thinking about to coordinate the behavior of a bunch of, you know, maybe unsophisticated downstream consumers of information is that rather than telling them what to do, we're just going to forecast what the state of the world is. Like we're gonna like guess. Like rather than saying here's the path you should take in this graph in this, you know, routing game, say, I'll say, okay, you know, I've like applied all of my fancy machine learning, and this is what I predict the, you know, like congestion is going to be on each road in Philadelphia tomorrow morning at 8 a.m. Okay. Now, what is the decision maker to do with that? Well, they could pretend it's correct and best respond to it, but they could do other stuff too, right? Like in principle, what they could do is choose some arbitrary policy. They were trying to be clever. What's a policy? Well, maybe it's something mapping the predictions we make, which let's assume is their only source of information now. Otherwise, they could do other stuff. But mapping the predictions we make, the information we give them, to the thing they should do. Okay, there's a lot of such policies, and you know, like depending on how sophisticated these agents are, like they might want to themselves solve some learning problem that sort of corresponds to figuring out what is the best policy. What's the mapping from predictions to actions that would be best for them? Okay. Okay, so fixing a prediction space C and action space A a policy is just a mapping. I'll call it P from predictions to actions. Okay, so I predict something. Here's what I think is the payoff relevant state of the world. You decide as a function of that what to do. That's a policy. And a particularly simple policy is going to be sort of focal for us. And that is sort of the straightforward policy of just trusting our predictions and doing the thing that would be best for you if our predictions were actually correct. Okay, we'll call that the best response policy. Okay, so for a utility function u, the best response policy is the policy that I'll write like this. Okay. The best response policy for utility function u, given some prediction of what the state is going to be, s hat, is just to compute your best response action given the possibly incorrect belief that the actual state that's going to be realized is our prediction, is s hat. Okay, so it's just going to choose the action amongst all of the available actions that maximizes utility function u, assuming, possibly incorrectly, that the realized state of the world is going to be s hat. Okay? Yeah. Sure. That's right. That's right. So I'm going to add extra information to the interaction. So previously, there you were playing this like online shortest paths, a game or something. What happens? Every day you need to choose an action, a path, and then at the end of the day, you learn what the state was, what the costs were for each of your actions, the congestion on the road. And you could do this however you like, and we gave algorithms like follow the perturbed leader that if you ran them would get you no external regret. So here, it's the same setting, except now there's additional information. Before you choose what action you're going to take, some centralized coordinator like sends you a message. It's like, hey, I predict the state's going to be s hat. And now you've got information that you can use at your discretion to help make the decision. So maybe, for example, if you didn't bring your laptop with you in your car, and so you're not able to like update, follow the perturbed leader when you're deciding like where to go, instead you can just like, look at the traffic map and take what looks like the shortest path, even though you know that the traffic map you're being shown like is a extrapolation, it's a prediction, right? Like they don't know exactly what the traffic is going to be at the time that you arrive at a particular road in this thing an hour into your trip, right? It's a projection. Nevertheless, it's a lot simpler for you to just sort of like best respond to this projection than to try to follow the perturbed leader. So that's the. Oh, the state will still be observable at the end. It's just that now there'll be there's a prediction of the state that's observable before you make your decision. And so although like maybe you could have follow the perturbed leader, you still have the information available to do that. There's this conceptually easier thing you can do if you want to. We're not necessarily assuming that, right? So like the state, right? Like it could be something that is generated as a function of the cumulative decisions of a bunch of play in a strategic game, right? So like, I think the sort of online shortest path example is like a good one. Although the road congestion on every road is a sufficient statistic for you to figure out what is your utility for playing each action, like it's not like weather. It's not like something that just happens. It is something that arises as a function of the decisions of all of the players in the game. That's why you can't know it before everyone makes their decision, and why forecasts might be needed. That's right. So like, like, so now you've got, like Google Maps or Waze in your car, and it's, like you could always just have like, listened to like the, I don't know, radio broadcast after the fact of, traffic during rush hour yesterday, and updated follow the perturbed leader. But now, like if you want, you can like best respond to the forecast. Good question. Other questions? That's right. Yes, we haven't quite like written down the full model yet, but that's exactly right. So sort of the interaction you should have in mind is that, it's again, as we're used to, like a sequential interaction in T rounds. Every round, first you see a prediction. Then, as a function of that prediction, using a policy, you choose an action. Then you see what the real state of the world was, which is probably different than the prediction. And then this repeats for T rounds. Okay, and so, yeah, and so like the change in perspective we have now is we're going to start to think about how we should design the algorithm that makes these predictions so that we coordinate good behavior, rather than thinking about the problem faced by each of the agents. If they were just given feedback about the payoff relevant state of the world at the end of each round, what should they do? We've sort of answered that question for individual agents. Those are all these no regret algorithms we've derived. Now we're thinking about the problem of like the coordinator who gets to make these predictions. How should he make predictions so that good things emerge? Good questions all. Does this make sense? Okay. Okay. Yeah, so the idea is, we make predictions, people act on them according to some policy. And there might be many downstream agents. After the fact, given a particular sequence of predictions we've made and given a particular sequence of realized states of the world, as a function of the policy that the downstream agent used, we can evaluate all of the same quantities we've been talking about when designing algorithms for the agent. For example, we can evaluate their external regress. Okay, so let's just mention that. So fix a sequence of predictions I'll call those S hat of T, and outcomes, I'll call that S of T. Okay, so the real outcomes are just S. The predicted outcomes, which are not real outcomes, they've got hats over them. Okay, and let's also fix a policy P for a decision maker with utility function U. Then the induced regret of our predictions, the induced regret to action A is just the sum over all time of the utility that this downstream decision maker with utility function U actually would have obtained had they played action A every day. Okay, so this is the utility they actually would have obtained, so it's measured with respect to the actual realized states of nature, compared to the utility that they obtained by applying this particular policy to the predictions that we made. Okay, so compared to the utility that they obtained by, instead of choosing action A every day, instead choosing the action that the policy tells them to choose. So the policy, which is a function of our prediction, But again, as measured, right, the policy chooses an action as a function of the prediction, but again, like how well they actually do depends on the realized outcome, not on the predicted outcome. Okay, so it's just, we make predictions. There's some sequence of states. A decision maker chooses their actions as a function of our predictions. We call that thing a policy. But still, like, they've taken actions that they're, they've had utility. And so ex post, they can like wring their hands about how much they regret having, just played some fixed action A, say, right? Like they can be like, should have just played action A, would have done much better than following this policy. Yeah.
So you could think of any fixed action like I started designing policy.
Yeah, we'll get there. So you can talk about. Okay, good. So we're going to work our way up to this, but this is just sort of the equivalent of external regret. This is saying how much you regret playing a fixed action. Now, of course, we could define using all of this notation for an arbitrary downstream agent if they pick some policy. All of the kinds of regret we've talked about. You could define swap regret for the downstream agent. And then you could even, and I think this is what you're getting at, talk about their regret to any other policy, right? Like rather than saying a fixed action, you could be like, oh, I should have played some other policy P prime that would have mapped predictions to actions in a totally different way. As we'll see, actually, this is stronger than swap regret. This implies that they have no swap regret. Any sort of swap function after the fact could have been applied with a policy, but you can do things that you can encode things, right? Because a policy might map two different predictions to the same action, and policy regret compares swap regret can only swap that action. Once the policy merges two predictions in terms of the same action, swap regret never gives you a benchmark that unmerges them. Whereas regret to the best policy could make the decision not to merge. Okay, so we will eventually ask the question, how can we make predictions so that essentially amongst all policies, the best response policy is a dominant strategy, meaning the best response policy will have no regret to any other policy. So we'll answer that question, but not yet. Does that make sense? Okay. Okay, so does this sort of make sense that we make predictions, like we make a single set of predictions, there's this single stream S hat, but now there's these different downstream decision makers who have different utility functions. They might be using different policies. And now as a function of the single stream of predictions, we can ask for each of the decision makers, what was their regret? Okay, it depends on what policy they were using. Now, the best response policy is going to be sort of a focal policy for us. We'll be like, in general, like we're going to analyze what happens if people play the best response policy. The best response policy is a very natural thing to do, right? Like you get Google's forecasts for what traffic's going to be like tomorrow. You probably try to pick a path, pick a route that minimizes predicted traffic, as opposed to saying, I know like a way in which Google's predictions are just systematically wrong. Whenever it predicts that there's no traffic on this particular road segment, what that means is that there's this secret path somewhere else in the network that's great. Right? Like in principle, there might be regularities like that you could do, but exploiting them might be difficult. And so a very natural thing for people to do is to best respond. And so we'll start by studying what we can do under the assumption that people best respond, okay? Without worrying too much about whether it's in fact a good idea for them to best respond, or whether there might be these sort of systematic errors in our predictions that would allow them to do something else more clever. Then we'll ask the question that maybe Eshwar was getting at, which is, well, like maybe some of the users are pretty sophisticated, in which case it doesn't seem reasonable to assume that they're going to best respond if that's not a good idea. And so then we'll ask the question, okay, well, how can we make sure not just that they have no regret if they best respond, but that if they best respond, they in fact have no regret to any other policy. There's no other policy they could have applied that would do better. Yeah.
Already, the policy is not good.
It could be a mixed strategy. The best response policy without loss of generality is not, but in principle, yeah, in principle, you could allow the policy to best respond to play some mixed strategy. We're never going to need to grapple with that because when we talk about regret to the best fixed policy, once you fix in hindsight a particular set of predictions and outcomes, the best policy in hindsight never randomizes for the same reason that if my opponent has already decided what to do in rock, paper, scissors, say, and I'm just best responding, I never need to randomize. Yeah. Yeah. So we're gonna continue to live in our favorite adversarial environments. So, we, the algorithm designers, are going to be thinking about how to generate the forecasts S hat, but the actual states of nature are going to be generated, we assume, by adversaries who can be adaptive to what we're doing and so on.
Does it imply that if you have a game like the there's a sort of utility the policy everyone thinks that
yes, with some caveats. So let's see. Okay, let me mention the caveats up front. Okay, so first of all, we are going to see a way to make sure that amongst all policies, the best response policy is like a dominant strategy, has no regrets to any other policy. But that way is going to scale very poorly in the dimension. So it's not an algorithm you'd want to run for online shortest paths. We will see results for online shortest paths, but they will be weaker than promising no policy regret. Second, okay, but maybe you don't care about running time and stuff. So fine, you make for all of the players the best response sort of a dominant strategy in policy space in this game. Policy space is not the same thing as algorithm space. What is a policy? A policy is just a mapping from predictions to actions. And in particular, if you're playing a policy, you map the same prediction to the same action no matter when it occurs. Now, in principle, you could do richer stuff than that. You could map the entire transcript of what's happened so far to an action. The strongest thing we're going to claim when we get to calibration is that it makes best responding a dominant strategy amongst all policies. That does not mean it is a dominant strategy amongst all algorithms, which would be a much stronger thing. Presumably. It seems really hard. Yeah, so in general, an algorithm, takes as input the entire history of what's been observed so far. So and there's really a lot of algorithms, and you could try to, it's a big space, so it's hard to, or maybe you'll do it, but like the technology I know of up until now makes it hard to say strong things about algorithm space. Yeah. If agents don't know their utility function. Okay, so let's see. So, okay, the most straightforward answer to your question is like no. So we're going to be like working in this model, agents like know their utility function. Now, maybe a less straightforward answer to your question is maybe, in that what does it mean that you don't know something about your utility function? Well, you know something about your utility function, and then there's other stuff about it you don't know. So you might, in various settings, be able to sort of just model that as uncertainty about the state, right? Like maybe the thing you don't know about your utility function is incorporated in this state. But like the model we will be working in is that the downstream agents have the ability to compute this best response function. So they would know their utility function. They would know what action would be best for them if only they knew all of the information in the state. Okay, good. Makes sense. Okay. Okay, so let's start with trying to think about maybe the easiest version of this class of problems that we've described now. Okay, so what are the various things we've at least talked about, if not written on the board? We've talked about making predictions that give fancy kinds of regret to downstream agents, things like swap regret. We've also talked about the incentives they might have for playing the best response policy. Like maybe we want it to make it a dominant strategy for them in policy space to best respond. But let's do neither of those things first. Let's just think of a very simple way to predict the states so that if agents best respond, we're not going to assume they will. We're not going to promise them anything along the lines of it being, a really good idea for them to best respond. We'll just say if they best respond, then they will have regret guarantees of a simple sort. They will have no external regret. Okay, so that's going to be the first problem we think about. How can we make predictions so that if the many downstream agents, whatever their utility functions are, happen to best respond, which is at least a natural thing for them, for unsophisticated agents to do, then this quantity will be small for all actions. They won't have been able to do better, at least by playing any constant actions. Maybe they could have done better by deviating in more sophisticated. Okay, that's the first problem we're going to solve. And the way we're going to solve it is going to be by doing something that, like once you see it, you'll be like, oh, like, of course. We're just going to do something that is basically going to force them, by best responding, to follow the perturbed leader, which is going to give them no regret guarantee. Okay, so like we have all of these algorithms that we've derived over the course of the course, that if the downstream agents play them, they will get good regret guarantees, bound quantities like this. Now we're saying, okay, we don't have direct control over what each of them are doing. We are producing some forecast S hat that is going to induce a particular downstream action. The first thing we might think of doing is just, now that we understand how our forecasts are going to induce the downstream action, we might just think of making our forecasts so that the downstream actions happen to look a lot like what they would have been had the agents been running no regret algorithms. There's various no regret algorithms to choose from. The difficulty, of course, we face is that we don't know their utility function. Okay, but follow the perturbed leader is going to be an especially easy one to adapt to this setting. Okay, so let's call this state perturbed. Follow the perturbed leader, or maybe just FPTL. Okay, so remember, what did follow the perturbed leader do? Follow the perturbed leader had sort of a different type signature because it was an algorithm for deciding what an agent with a particular utility function should do at each round. So what follow the perturbed leader did is it sort of said, okay, I know what your utility function is because you're the one running me. I'm just going to compute what utility you would have gotten for each fixed action in hindsight. I'm going to add noise to those utilities, and then I'm going to play the thing that has the largest noisy utility. Okay? We don't know anymore. Oh, so like that's just a different type signature than what we need to do here. Like we're not outputting actions. We want to induce different actions in different players. We're outputting predictions. But, like follow the perturbed leader already sort of took actions that were of this form. It was like, play the thing that was the best response to something, to sort of a noisy utility function. And we can't add noise to the utilities. We don't know what the utilities are. But remember, we've assumed that the utilities are linear. So what we can do is add noise to the states. And because of the linearity, adding noise to the states is going to be a whole lot like adding noise to the utility function for each of the downstream decision makers, no matter what their utility function is. So that's the idea. This is going to be the algorithm used by the forecaster, exactly. Okay. So, okay, so it's super simple algorithm. What the forecaster does in each round is predict that the state today is just the empirical average of the state that has been observed to occur in the t-1 previous rounds. Okay, if we just predicted that, this would sort of be like follow the leader. We know that's not a good idea, so we'll add some noise to it. Okay, we're here, just as in follow the perturbed leader. The noise is just a d-dimensional vector of uniformly random entries between 0 and 1. Sorry, between 0 and 1 over epsilon, where epsilon is a parameter we get to choose. Okay, so super simple. We're just going to predict that the thing that's going to happen today is the average of what's happened in the past plus some noise. Okay, so the traffic in the road network today is just going to, like, what's it going to look like this morning? Well, it's going to look like what it always looks like, plus a little bit of noise. Okay, yeah. Let's see. So you might want to do that if you were going for something stronger, like adaptive regret, like regret over different windows of time. But like I think the best intuition for this, rather than trying to like produce intuition from whole cloth, is to like go back and remember all of the intuition that you now have for follow the perturbed leader. And what is this doing? This is basically trying to trick agents who think that they're just like doing something simple and best responding. It's trying to trick them into playing follow the perturbed leader, which has regret guarantees. Okay, and what does follow the perturbed leader do? Follow the perturbed leader just looks at your cumulative payoff for each action in hindsight over all of the rounds from round 1 all the way up through yesterday, adds noise to the payoffs and does the best thing. Here, like the noise is being added to the states rather than the payoff. Does that make sense? Okay, so it's like, to the extent that there's intuition here, separately you can ask, what's the intuition for follow the perturbed leader? That's reducing to a previous problem. You should have asked questions about that, last month or whatever. The intuition here is that we're just tricking people into playing follow the perturbed leader. Basically going to be for online linear optimization. The utility function is linear in the state. So this is basically online linear optimization. Exactly. And we'll see from the analysis, it's like almost exactly the same thing. Like we're using a property that follow the perturbed leader happens to have that this would be more difficult to do with multiplicative weights. We're using a property that follow the perturbed leader happens to have that like, it's really just best responding to sort of a, these utilities plus noise. And because the utility functions are linear, it doesn't matter so much whether you add the noise like to the thing you plug into the utility function or outside of it. That's because of the linearity. Does that make sense? So we're not this thing is it's not going to solve a more general problem than follow the perturbed leader. It's just that now we sort of, to the extent that you need to be a little bit sophisticated to add noise, now we just need like the central planner to be a little bit sophisticated. Everyone else thinks they're just best responding. Yeah. Yes.
Yeah.
Well, so that's the thing, right? Like we don't know what the downstream utility functions are, so the algorithm doesn't incorporate them, right? The claim is going to be, however, that when downstream agents look at these forecasts and best respond, whatever the utility functions are, they will turn out to have no regret. But right, that like there's no mention of like utility functions in this algorithm. That's like the whole point. Like we don't know what the utility functions were. If we did, then we could just run follow the perturbed leader as originally presented. Good. Other questions? The object of the forecaster is that we should be able to point to any downstream agent who has any utility function. We should be able to say, if that downstream agent is best responding to our forecasts, then it will be as if they had played follow the perturbed leader. They will have no regret to any of their actions. Exactly. The noise is important for the same reason it's important in follow the perturbed leader. Because otherwise, rather than tricking them into playing follow the perturbed leader, we'd be tricking them into playing follow the leader, which is not a no regret algorithm. Okay. Okay. Okay, so here's the claim. Fix any utility function. Mapping actions and states of the world to payoffs between 0 and 1 that we assume is linear and L Lipschitz in its second argument. Then for any sequence of states, which can be chosen by an adversary, so for any sequence S1 through ST, the decision maker with utility function U playing a best response policy the forecasts generated by state perturbed follow the perturbed leader has regret at most. Well, the maximum over all of their actions of the sum over all of the rounds of the degree to which they regret not having just played action A every day, given the realized sequence of states, in comparison to what they actually did, which was play the best response policy. So every day what they actually did was they played the best response policy given their utility function, 2-hour forecasts made over there, given the actual realized state. This is at most something that's going to look like a follow the perturbed leader bound. L over epsilon plus 2c epsilon t, which epsilon is the parameter we get to set. Epsilon's the the sort of noise parameter. If we set that optimally, can be made to be 2 times the square root of 2clt, where what are all these letters? Well, C is just the maximum norm of any state, the maximum L1 norm of any state that might be realized, and L is the Lipschitz parameter of the loss function. Okay, so you get sort of a root T regret bound. For reasons that maybe are not that surprising, you're basically causing the agent to follow the perturbed leader, but sort of the interesting qualitative thing that is sort of new in this theorem compared to what we've been doing all semester is that the algorithm has no idea what the utility function is. The algorithm is not defined in terms of the utility function. It's one set of predictions. This theorem is universally quantified over all utility functions. That one set of predictions will simultaneously guarantee, no matter what the utility function is of the downstream agent, that their external regret will grow only with root T. Okay, does that make sense? So this is a particularly simple case where like the way you do it is maybe, once you see the algorithm, you can sort of figure out what the proof is going to be. But I think it's worth noting this new qualitative aspect of the theorem, which is pretty neat, which is that one algorithm, yet a universally quantified guarantee over all possible downstream agents who might be making use of this information to take actions according to their own interests. Okay, does that make sense? Okay. So we're going to analyze this very much like we analyzed follow the perturbed leader, because it is follow the perturbed leader. We just have to be a little bit careful because it's not quite follow the perturbed leader, right? Follow the perturbed leader was adding noise to the utilities of each of the actions. Here we're adding noise to the state, and we just need to make sure that doesn't break anything, but it doesn't. So just like for follow the perturbed leader, our analysis of state perturbed follow the perturbed leader will proceed by analyzing a series of fictional algorithms. Okay, remember, how did follow the perturbed leader work? Well, first we sort of imagined that we could look into the future, see what was going to happen today, and then not add any noise at all, and just play be the leader. And sort of remarkably, well, maybe not that remarkably, because it's impossible to do it, but remarkably, if you could do it, you'd have actually 0 regret. And then we said, okay, well, not adding any noise at all, that's maybe not fair. Let's say we can still look into the future, but I'll also add noise. we analyzed B, the perturbed leader. And we said, okay, well, adding noise was sort of a dumb idea. If you could look into the future, B, the perturbed leader doesn't have zero regret, but it has regret that's not that big. You can bound the regret in terms of how much noise you add. Why did you add noise? Well, that was because of the third step of the proof. For the third step of the proof, you said, okay, well, follow the perturbed leader is actually not that different from be the perturbed leader, right? The noise kind of washes out the difference. So actually the distribution on actions played by follow the perturbed leader is very close to the distribution on actions played by be the perturbed leader. The noise washes out the only difference, which is the contribution of this last round utility to your computation. And therefore, the regret bound of follow the perturbed leader can't be that much worse than the regret bound of be the perturbed leader. That was how the analysis worked. Okay, so we need to check that that all works here too. And so we're going to talk about the corresponding state perturbed version of those like fictional algorithms. Okay, so let's say that the algorithm state be the leader is the following. And I'll just, the real algorithm, state perturbed follow the leader, those are going to have hats on top of the predictions. I'm going to put like different headwear on top of each of the predictions. So for state be the leader, I'll put like a bar on top of the predictions. The predictions made by state be the leader are just the empirical average of the states that have been realized so far. Okay, just the average. But like crucially, they're the average not from day 1 through yesterday, but from day 1 through today. Okay, so you can't implement this algorithm because we don't know what today's loss is. Okay, but it's state be the leader, just outputting the average of what's actually happened up through and including today, no noise. Okay, we'll also have state perturbed be the leader. Be the perturbed leader. And the predictions made by this fictional algorithm, I'll put a twiddle on top of. And these are going to be the empirical average again over all of the rounds up through and including today. So another impossible to implement algorithm. But now I'm going to add noise to them. Same kind of noise we're adding in the real algorithm. Just uniformly random in each coordinate in the range between 0 and 1 over epsilon. Okay. Okay, so the plan of attack is going to be to say fictional algorithm number 1 causes any downstream agent to have 0 regret. Fictional algorithm number 2 causes any downstream agent to have only small regrets, where small is controlled by the amount of noise we're adding, 1 over epsilon. And plan of action number 3 is going to say that the real algorithm, actually, if epsilon is small enough, if we're adding enough noise, is sort of playing something that is sort of every round indistinguishable from what this fictional algorithm is playing, and so its regret bound can't be too much worse. And chaining together those 3 claims, each of these claims we've previously proven for follow the perturbed leader. We just need to verify that each of these claims still holds in this form where we talk about any downstream agent. Okay, it's the plan of attack. Yeah. Oh, I think I just made a mistake then. I didn't mean to, I just wanted it to not be in the sum. So let's see. Yeah, like you sum these things up, you add noise, you divide by t. I don't want you to add like t noises. Okay, good. Okay. So let's prove the first lemma, or let's state the first lemma. Okay, so for all utility functions that look like they do in this theorem, so for all utility functions mapping actions and states of the world to zero, to utilities between 0 and 1, still assuming that it's linear in Lipschitz and its second argument, and for all sequences of states of the world that might be chosen by an adversary. If I look at, and for all actions A that our decision maker with utility function U might have regret to, if I look at the regret that the decision maker actually has over T rounds to what they would have obtained had every day they played action A, given the realized state, and compared that to what they would have done had they been best responding to S bar T, the sort of be the leader analog. Okay, can't do this. This is the fictional algorithm. But if they could do it, then their regret would actually be 0. Okay, so like if only we could make predictions with 1 day look ahead, everyone would have 0 regret. Okay. So how do we prove it? Well, we don't want to reinvent the wheel. Like, remember, we've already proven that if any particular decision maker is playing be the leader, then they will have no regret. So we just need to prove that the best responding decision maker is exactly playing be the leader in this scenario. Remember, what is be the leader? Be the leader is just the algorithm that looks for each of your actions A, what utility you would have gotten had you played A consistently from day 1 up through T, and just plays the thing that has highest utility. Okay? That's be the leader. So we already proved when we analyzed follow the perturbed leader that that policy always has 0 regret. So we just want to make sure that best responding to this state forecast induces exactly that play. Yeah. Because it's not like exactly the same, because the Lipschitz constant, and so like it is exactly the same when you don't add noise. The noise causes the algorithm to be a little bit different, not in a way that is meaningful for the analysis, but it's not exactly the same algorithm. And so, but maybe there's a more direct proof where you just sort of do that. The best way I could think to recover it, and this is, by the way, the sort of this is like the U calibration results on in the last few pages of the U calibration paper. Also, the way they prove it is sort of by just reproducing follow the perturbed leader analysis. Yeah, it would be nice if you could just say, like, the downstream decision maker is just playing follow the perturbed leader, the same way you can say that in this hypothetical world, the downstream decision maker is literally just playing be the leader. But it's not quite true, I think, because depending on what their utility function is, the noise you're adding might be a little different. Yeah. Okay. But yeah, maybe there's a more direct way to do this instead of repeating these arguments. Okay. Okay, so this is going to follow just from the linearity of the utility function in the state. Okay, so we know for every action A that the utility that this agent will get if they play action A and the true state were in fact the prediction S bar of t is, well, let's just unroll what the prediction is. It's the utility if they play action A and the true state is the empirical average from day 1 up through today of the realized state. Okay, because that's all the predictions are for B the leader. It's just the empirical average. And the utility function is linear for any fixed action A, linear in the state. And so this is just, we can take the sum outside of the utility function. It's just the average over all of the days of the utility of the realized state at day t prime. And so it doesn't matter whether we choose the action to maximize this or to maximize this. It's the same thing, right? So, the thing that we're actually doing, the thing that the agent's actually doing, which is playing the best response policy to these average predictions, S bar, that's the same thing as choosing the action that maximizes the average utility of playing action A given the realized states from days 1 up through today, that is B the leader. And so, whether we forecast the average of the states and then best respond, or whether we best respond to the average of the states, doesn't matter. This is just, this fictional algorithm is just inducing all of the downstream agents to play what they would have played had they been playing that other fictional algorithm we already analyzed, B the leader. Okay, so we already proved for each of them that they have no regret. Okay, here we're sort of important that the utility function was linear. That's what leads to the fact that we can sort of work in state space, but get every downstream agent, despite the fact that they have different utility functions, to do the thing that they would have done in utility space. Okay. Next fictional algorithm. Okay, so yada, 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 same hypotheses as before. Fix any utility function that looks like this, that is Lipschitz and linear in its second argument. Then for any sequence of states, again, that can be chosen by an adversary, if we look at the regret that a downstream agent who's playing the best response policy will have, to any action A, given the actual realized states, if what they did now is actually played a best response to the state perturbed be the perturbed leader forecast with twiddles on top. Given the actual realized states. that their regret, okay, it's not going to be 0 anymore, but it's going to be bounded by L over epsilon, where L is the Lipschitz constant of the utility function. Okay, that's the claim. Okay. So again, we've proven something similar already for B, the perturbed leader, when we got to work directly in utility space. So we just need to make sure that what we proved there remains true here, where the only difference is the perturbations are being added in state space rather than utility space. Yeah, so the perturbations in state space will potentially have magnitude scaling with L, blown up by whatever is the Lipschitz constant of the utility function. Okay. So if you remember what was sort of the main trick there, it was to sort of note that since we're just talking about expected regret, rather than thinking of an algorithm that adds noise separately at every round, we could just think of an algorithm that adds noise once at the beginning. Okay. So yeah, so the point is, if I look at my expected regret, or even really just my expected utility, I'm gonna write the prediction now, just to be careful about this. I'm gonna write the prediction as a function of the noise variable. Okay, so because we're gonna change, we're gonna do something sneaky with those variables. So the predictions that we're making using state perturbed, be the perturbed leader, are functions of these realized noise variables. Okay. But my expected utility, if I follow this best response policy, since it's just a sum of my utilities over each round, it is, by linearity of expectation, the sum of my expected utilities. So this is just the sum over all of the rounds, where at each round, my expected utility is a function only over the noise random variable I draw for that round of the utility that I obtain when I best respond to the prediction made at that round, given the state realized at that round. Okay. And then I just note that each of these random variables, n1 twiddle, n2 twiddle, n3 twiddle, they're all distributed identically. Okay, and there's no interaction terms. And so equivalently, I could just sample one of them and use that to plug in every term. Since the marginal distribution on each one is the same, that's not going to change the expectation. Yeah. Exactly. That's exactly right. So yeah, so the claim is at this step now, if I just have a single random variable that is distributed the same way as each of these, and I take the expectation over that random variable, that doesn't change the expectation, right? And if you want, yeah, it's a coupling between these two distributions that differ in their joint distribution. Like in the real algorithm, I'm sampling a different noise variable at each round. Here, in this analysis now, the noise variables are all coupled to be identical, but none of the terms that I cared about and what I need to prove depended on more than one at a time. So because the marginal distribution is preserved, the expectation is unchanged. Okay, that's, yeah, what's going on there. Okay. Okay, I have 1 minute left, so rather than finishing the algebra, let me just narrate the rest of the proof. So, sort of similarly to our original analysis of be the perturbed leader, once we're just adding noise once and using the same noise every time, we can equivalently think of that as just having at the very beginning added a perturbation to the first state. Okay? Rather than re-randomizing every time, I could just think of adding a perturbation to the first state. The same algorithm. But if I'm just adding a perturbation to the first state, I'm really just running state perturbed be the leader without perturbations, just for an alternative sequence of states where the first state was changed and had this noise added to it and the others didn't. Okay? So I have no regret to that fictional sequence of states. But that fictional sequence of states only differs in the first state. How much does it differ? Well, I might have perturbed every coordinate of the state by up to 1/epsilon. But my utility function is L Lipschitz in the L infinity norm. So how much is that going to change my utility and therefore increase my regret? At most L/epsilon. Okay. And finally, the last step of the proof. Well, what did we rely on in our analysis of follow the perturbed leader? That the distribution over play for be the perturbed leader was close ultimately in like total variation distance to the distribution over play for follow the perturbed leader. There, that was accomplished by maximizing over noisy utilities. But here, it's actually even simpler. The best response is done on the noisy state. So if the two distributions on states produced by state perturbed be the perturbed leader and state perturbed follow the perturbed leader, if those are close in total variation distance, then just because the actions are a post-processing of that, they too will be close, like an information processing inequality. And we're adding the same kind of noise to the states. And so the distribution over predictions in state perturbed be the perturbed leader and state perturbed follow the perturbed leader, those are close in total variation distance. Therefore, the distribution on any sequence of actions that is derived from them must also be close, and therefore any expectation computed as a function of these things, in particular expected regret, has to be close as well. Okay, that's it. You string together those three lemmas, you get the theorem. I think it's the only place we actually use linearity is really the first lemma, the fact that I don't think we're using it. There we're using Lipschitzness. Here we're not using it. Here we're just using that regret is a sum over stuff. But like, because each term in the expectation is an expectation over a single term. That's why we can swap out. That's why we can couple the random variables. We don't need that it's linear here. We also don't need that it's linear when we say follow the perturbed leader is close to be the perturbed leader, because we're just saying the distribution on predictions is close. I think the only place we really use linearity is that when we predict the one look ahead predictions that are just the empirical average, there we use linearity to say best responding to the average of the predictions is the same thing as playing be the perturbed leader. So that's the only place we're using linearity. All right, I'll see you guys next time.